After
Cobalt, the oxidation state of cobalt is +3, that is D6. I told you that for all cobalt 3 complexes are low spin complex except KCCOF6 and COF3 H2O3 times. So all will be, both will be low spin.
expected.
As soon as you have low spin, that means it will be diamagnetic.
Yes. Yes.
It will give you D2sp3 hybrid, not sp3d2. Because except two complexes which I have told you, for cobalt 3, all other, whether it's water, ammonia, hydroxide, all will give a low spin octahedral complex. And how do I know low spin? Because it is diamagnetic. Had it been paramagnetic, then I would have said the interaction is weak, so it is a high spin complex. So the two high spin complexes are paramagnetic, and except those two, all cobalt 3 complexes are diamagnetic and they have D2sp3 hybridization. Okay, now we go to, is it clear to all of you?
Yes.
Now write down the isomerism of coordination octahedral complexes. Coordination isomers. Write down exchange of ligands. Exchange of ligands between cationic and anionic complex. Between a cationic and anionic complex gives rise to coordination isomer. Exchange of ligands between cationic and anionic complex gives rise to coordination isomer. Example. In the first case, ammonia was part of a cationic complex. This was cationic complex. Because ammonia is neutral, Cobalt has 3 positive charge. So charge of the complex will be 3 positive. So it is a cationic complex. Here, the cyanide has a negative charge, -1. So you have 6 negative, you have 3 positive. So you have 3 negative charge. So this was an anionic complex where the charge of the complex is negative, it is an anionic complex. Where the charge of the complex is positive, it's a cationic complex. Now what has happened? The ammonia has exchanged from cobalt has gone to chromium. So chromium formed an anionic complex. Now chromium forms a cationic complex. And cobalt, which was a cationic, now it becomes anionic. So the ligands have exchanged between the cationic and the anionic complex. That leads to coordination isomer. Is it clear?
Yes, sir.
Okay?
Yes, sir.
Okay. Sulfate was in the coordination sphere. Chloride was in the ionization sphere. Now the chloride is in the coordination sphere, sulfate is in the ionization sphere. How do I know that the sulfate is in the ionization sphere? If I add barium chloride, there will be no precipitation of barium sulfate.
Yes.
If I add barium chloride, I will get immediately precipitate of barium sulfate. But if I add silver nitrate, there will be no precipitation of silver chloride. In this case, if I add silver nitrate, immediately the silver chloride will precipitate. The white precipitate will pop. That indicates that whether the chloride is within the coordination sphere or not. Similarly, so the exchange of ions between coordination sphere and ionization sphere gives rise to ionization isomers. Okay?
Yes, sir.
Hydrate isomer. Hydrate isomerism, write down, a complex having same molecular formula but having different number of water molecules within the coordination sphere. Gives rise to hydrate isomers. I'm repeating. A complex having the same molecular formula but having different number of water molecules in the coordination sphere gives rise to hydrate isomers. For example, if I have a complex with molecular formula CrCl3 6 water, that means chromium is to chlorine, is chloride is to water, is 1:3:6.
Yes.
What are the possible hydrate isomers? One is
CrH2Cl.
all water molecules were in the coordination sphere. In the second case, 5 are in the coordination sphere, 1 in the ionization sphere. And the third case, 4 is in the coordination sphere, 2 is in the ionization sphere. So they are called hydrate isomers. Now we come to the the fourth category.
So please wait.
Okay, tell me when you are finished. When you are ready. Have you written all of you?
Yes.
So without making a change in chlorine inside and outside the coordination sphere, will that be similarly classified as hydrate isomer?
Can you repeat the question?
Here in the examples you have also removed chlorine respective to the H2O inside and outside the coordination sphere. If we just remove the H2O,
Chloride is an anion. Hydrate word is used means water molecule. It's nothing to do with the anion. These isomers are depends upon the number of water molecules within a coordination. Okay?
yes,
Not
yes.
the other ions which are present. Don't worry about it. It is the how many water molecules are in the coordination sphere that gives you the hydrate isomer.
Yes.
Linkage isomerisms will be exhibited by ambidentate ligands only. What is ambidentate ligand?
Different types of ligands.
fourth category of isomers is linkage isomerism. This is shown only by ambidentate ligands. Linkage isomerism is shown only by ambidentate ligand. Ambidentate ligand is defined as a ligand which has more than one potential donor atoms, but only one of them forms a coordinate bond with the metal ion at any point of time. Okay. If you look at thiocyanate, what is the structure of thiocyanate? Thiocyanate ion has a structure like this. The sulfur has the two lone pairs. Nitrogen has also two lone pairs. Okay?
Yes. Yes. Yes.
Sulfur can act as a ligand. Nitrogen can act as a donor atom. So, when sulfur acts as a donor atom, it is called thiocyanate. Or when nitrogen forms a bond with a metal, it is called isothiocyanate. Or so the word, the letter which is written, S or N, indicates which is the donor atom. When N is written, that means the nitrogen atom of the thiocyanate is a donor atom. When S is written, that means sulfur is a donor atom, but both of them will never form the coordinate bond to the metal at the same time. Only one of them will form a bond. Similarly, when nitrogen is bonded to the metal, it is called nitro or nitrito hyphen N. When oxygen is bonded to the metal, it will call nitrito or nitrito hyphen O. So these are called linkage isomers. These are linkage isomers. In one case, the sulfur is bonded to the metal, and in another case, the nitrogen atom is bonded to it. You understood?
Yes.
Yes.
That means there are two donor atoms present in a molecule. But only one donor atom forms a coordinate bond at any point of time.
Yes.
Not both.
Yes.
That is where it is different from a bidentate ligand than an ambidentate ligand. A bidentate ligand forms two coordinate bonds at a time, simultaneously. Whereas here, only one of them forming a coordinate bond at any point of time.
Yes.
Now, so I have given you some examples like thiocyanate, isothiocyanate, nitrile, cyano, nitrile. When nitrogen is forming a bond with the metal, it is nitrile. When the carbon is formed in a bond with the metal, it is cyanide. Cyanide. Okay. Geometrical isomers of octahedral complexes. We'll start with a first when the ligands are dentate or unidentate ligands. Dentate means the number of coordinate bond the ligand forms, the metal. When the ligand forms only one, it's called monodentate or unidentate. So we'll start with when all the ligands are monodentate ligands, and the coordination number is 6. I have given you the coordination number and the geometry and the hybridization.
Yes. Yes.
I have told you that coordination number 6 gives 3 geometries. Did I mention?
Yes.
Theoretically, coordination number 6 can show 3 geometries. Octahedral, Hexagonal planar, just like benzene ring. Metal is at the center, the ligands are at the corners of an hexagon. That is hexagonal planar. Trigonal prismatic is for 3D metal. These are theoretical possibilities. Okay? So if somebody asks you coordination number 6 will show only octahedral geometry, is it true or false? Then you have to say it is false. But for your JEs, only 3D metals are included. And for 3D metals, when the coordination number is 6, it forms only octahedral geometry. No hexagonal planar, no trigonal prismatic.
Sir, although if the metal is 3D, but if the ligand is di-dentate, then the structure won't be octahedral.
Yes. There are only 3 bidentate ligands will be there. So, as long as it forms 6 coordinate bonds, it will form octahedral structure. There is no other structure possible for 3D.
With 3 ligands also. Yes.
You see the same structure I get?
Yes.
Yes.
So whether it's a bidentate or tridentate, as long as it forms 6 coordinate bonds, it will give only octahedral structure for 3D metals. Is it clear?
Yes.
Okay, now let us concentrate on this. If you have all the ligands are monodentate ligands and they are same. Okay? How many structures can be drawn for an octahedral geometry?
One.
Only one?
Yes. Yes.
The easiest way of drawing octahedral is draw 3 lines cutting at a point. Okay?
Yes.
ML51. How many structures will be possible?
3, 6.
Only one.
Yes.
Wherever you put Y,
Yes.
only one Y will be trans to L, and all L are trans to itself. Wherever you put Y, diametrically opposite to it will be L, and the remaining L will be trans to each other. Trans means 180 degrees opposite to each other. And anything other than 180 is cis. Remember that. That cis means other than 180 degree. 180 degree puts the two ligands diametrically opposite to it. Do you understand that?
Yes.
Okay. So, how do you say 6? There could be only one combination possible,
Yes.
where Y will be opposite to L and the remaining L will be opposite to itself. ML4Y2.
3.
Huh? 2. Y2.
One diametrically opposite and minus 90 degrees.
So, this is trans, this is cis. Cis means adjacent. Adjacent does not mean immediate adjacent. This is also cis.
Yes.
This was immediate. This is also cis, this is also cis, this is also cis. Only when it is here, it is trans. Anything other than 180 degree is cis. Okay? How do you differentiate cis from trans? How will you differentiate cis from trans?
Dipole moment.
Dipole moment will be trans, dipole moment will be,
0.
and it will have a non-zero dipole moment.
Yes.
But what Warner did is not from dipole moment. He said that if he reacted Ml4Y2 with a bidentate ligand, where the 2X occupies this adjacent site, replaces two Y's are replaced by one XX. Then he said that if this compound is obtained, that indicates the position of Y must be cis to each other. Because bidentate ligand cannot span across trans position. No. It can go only cis position. So,
Yes.
that means the position of Y must be cis to each other, which have been replaced by a bidentate ligand. When they are trans, it cannot be replaced by a bidentate ligand. So if a bidentate ligand can replace, do you understand nucleophilic substitution reaction?
Yes.
So if a bidentate ligand can nucleophilic substitution by nucleophilic substitution gives rise to a complex, then the position of Y must be cis to each other, and that is how we distinguish cis from trans. This is the most important part of now what I am discussing. Be careful, huh? If you have any doubt, you ask me. How many structures will be there for Ml3Y3 or Ml3Y2Z or Ml3XYZ? What are those two?
In all in one plane and two in one plane and one in the perpendicular plane.
What are they called?
All in cis, two.
When one of the ligand is 3 in number, when one of them is 3 in number, whether the other is 3 or not, all will be from facial and medial. Facial means all 3 identical ligands are cis to each other. And when 2 out of 3 so facial so when the ligands, same ligands, are cis to each other, they are facial, and when 2 out of 3 same ligands are trans to each other, that will give me meridional isomer. Okay?
Yes.
Now, you give me the of geometrical isomers you have to give. You see, there's 3 are common.
Yes.
3 ammonia. Immediately it is facial and medial. As soon as you see the same ligand 3 in number, you start in terms of facial and medial, not cis and trans. Cis and trans when it is L4X2 or L4Y2, not L3Y2. They are cis, but that does not mean they will be called cis. They will be called facial.
Yes.
So how many geometrical isomers you will have, and how many geometrical isomers you will have? Work out yourself and then give me the answer. You have to see the permutation and combination. How many combinations are possible for this. One is facial. How many facial isomers you will have? Only one. Wherever you put, the trans ligand is the same. Whereas does it change the trans ligand? Cl trans to ammonia, Cl trans to ammonia, F trans to ammonia. F trans to ammonia, Cl trans to ammonia, Cl trans to ammonia. So you will have only one facial isomer.
Yes.
What is your problem? I don't understand. What is difficulty? You have to see whether you have the same trans atom or not. If the same trans group are present, that means only one configuration is possible.
Yes.
How many meridional isomers are possible?
So if it is Cl, FCl, we have taken two chlorine together and one chlorine separately. Means Cl, if Cl, FCl is there then?
These are the two possible.
Yes.
Yes, sir.
Yes, sir.
So you will have two meridional isomers and one facial isomer. So the total number will be 3.
Yes.
Cl trans to Cl, Cl trans to F. You have 3 positions, you have 2 atoms. How can you place them? Chlorine trans to chlorine, chlorine trans to chlorine. Okay? Now you work out this one. What is this isomer? What is this isomer? How many facial isomers do you have?
One.
Okay. How many meridional you will have?
Three.
Three?
Yes.
So Cl trans to Br,
Cl trans to F.
Cl trans to F, and
Br trans to Cl.
Br trans to F.
Yes.
So facial you will have only one. Because wherever you put chlorine, bromine, fluorine, you will have only one structure possible.
Yes.
So facial will give you only one isomer. But meridional will give you 3 isomers. So the total number of isomers will be 4. Okay?
Yes.
How many geometrical isomers you will have?
Yes, sir. 4.
No.
3.
No.
7.
1, 2. 2 identical.
6.
Wrong.
So 3.
7. 5.
Structure, sir.
Where from you got the sixth one?
No, sir.
5 structures.
I counted the same two.
So, for you, if you have three types of monodentate ligands, each is having 2 in number, then it will call Cs. This is trans. B, A trans to A, B trans to B, C trans to C. So trans. A Cs to A, B Cs to B, C Cs to C. C. Trans. C. A trans to A, B and C are Cs. B trans to C, A and C are Cs. C trans to C, A and B are Cs. So there are 5 isomeric structures possible, geometrical, for these compounds. Okay. Any ligand which is more than one donor atom which forms a coordinate bond simultaneously, they are called multidentate ligands. Bidentate, tridentate, tetradentate. So ethylene diamine, this is your ethylene. And there are 2 amines, so it is called ethylene diamine. It forms 2 coordinate bonds, so it's a bidentate ligand. Okay?
Yes.
This is called there are two ethylene units. So it is diethylene. There are three amines. That is triamine.
Yes, sir.
So diethylene triamine is a what type of ligand? How many donor atoms it has?
Three.
So it's a tridentate ligand. So whenever the bidentate or a tridentate ligand forms a